Hi there. Welcome to this video on matrix algebra. This will be the very first lecture of the series. In this lecture, we will just give an introduction and an outline of the lecture series. So note that these notes were written by Alberto Bresson, and the lectures will be given by me. Let's get started. Now first, let's talk about textbooks. There are many textbooks available on the topics of matrix algebra. So if you want to have a reference book, the recommended one is the book by Thomas Shore, Apply Linear Algebra and Matrix Analysis, Springer 2007. In this video, we will give an overview over the topics that will be covered in these videos. There will be a series of them. So first, just a few words about how do you watch these videos. So the topics and the concepts will be introduced in a sequential way, similar to most of the math classes. So I will label the videos by lecture. So the best way is to watch them in a sequential manner. This is particularly true for beginners, that is, students and people that are not too familiar with the topic. If you are more advanced and you are interested in one specific topic, then you can pick up specific videos later to watch. Okay, so let's move on to today's overview. So a brief kind of a recalling of a linear system of equations, and these we have encountered possibly already in high school. So you have three unknowns, let's call them x1, x2, and x3. And they satisfy some relations. Let's say we have these three equations written out for these unknowns. So if you look at these equations, they are terms add up equal to some number. Okay? And then each of these terms has the form that it is the unknown, these x1, x2, and x3s, multiplied by a constant. So you see all the terms are like that. And if that is your equation, then this is a linear system. So a convenient way of writing this out in a more compact form is to use the concept of a matrix and a vector. So in these notations, what we can do is we can line up all the x's, x1, x2, x3, into kind of three columns, and we take their coefficients, that's the constant in front of them, take them out and gather into this block of 3 times 3 numbers. So if you look at the first row here, I have coefficients 1, 1, 1, and there I get 1, 1, 1. And then for the second equation, there is no x1, so it's 0 times x1. Then you will have 0, 2, 5, as we have here. And the third equation would be 4, 6, negative 8. Okay? And these are multiplied by the so-called the unknown vector, which is the unknowns, x1, x2, x3. They are in a column vector. And then equal the right-hand side, which is a vector, a column vector collecting these constants on the right-hand side. Okay, so if we call these matrix a vector, then this is a matrix, and this is a vector, and this is a vector. And we can denote them simply by one letter. Okay, so from now on, you will see very often we will write it as capital A times x equal b, where the A is this 3 by 3 matrix, and x is the unknown vector, and b is the vector on the right hand side, which consists of constants. So the ultimate goal of this course is to show some efficient ways to write and then to solve such a system by manipulations of the matrix A. And we will eventually have solution formulas, and then if this is a huge system, then the whole thing can be carried out by computer using numerical algorithms. Once you have a numerical algorithm, so how do you determine the efficiency of such an algorithm? In other words, we can do an operation count, meaning that each operation, which includes addition, multiplication, and divisions, how many of such operations are needed to solve a system? Let's say system X here has n unknowns. So depending on your algorithm, you will end up in different counts. Let's get a general idea of what a count means. So first, if you have an algorithm that takes about n factorial number of operations, then when n is large, n factorial is a huge number. This is a very lousy algorithm, you can say, because it will take forever for the computer to solve it. Okay, and then if you have another algorithm, somewhat improved, that takes n to the power 3 number of operations, and then that's a pretty good algorithm. Or you can do even better. Let's say you have n squared times log n. So you know log n does not grow as fast as n. So it's a smaller number here for a large n. So this would be an even better algorithm. So let's motivate our study by asking the question, that is, why do we want to solve systems of equations or large systems of equations? So we can take some example which we probably have encountered in high school or in freshman college math course. Say we have the following situation. So I'm interested in finding out the age of 3 persons, Alice, Ben, and Chris, and given the following. So the sum of their ages is 21, and I know Chris is 1 year older than Alice, and then Alice is twice as old as Ben. So how do I go about and solve a problem like this? Okay, so let's set up a mathematical model equivalent to this word problem. So let's call capital A, B, and C to be the ages of these 3 people, Alice, Ben, and Chris, conveniently. And then we write out these given assumptions into equations. So the first one says the sum of their ages is 21. That will mean A plus B plus C is 21. Okay, and the second one says Chris is 1 year older than Alice. So Chris, C here, is Alice's age plus 1. Okay. And the third one says Alice is twice as old as Ben. So A here is 2 times B. So we see that we have a system of linear equations where the unknowns are A, B, and C. Now it is also possible to write this as a matrix notation. So we collect the coefficients, and A, B, C gives me 1, 1, 1. And the second one, I will move the A to the left-hand side, and I get negative A. So I get negative 1, and B is 0, and C is 1. And then third equation is A minus 2B is 0. So A minus 2B, 0C is 0. Okay, so we have this 3 times 3 matrix, and the unknown is a vector A, B, C. And then the right-hand side are the constants, 21, 1, and 0, collected here. So probably you already know some ways of solving this from earlier studies, and also after a few lectures of this course you will also know how to solve this. So let's say we solved it, and then we have the solution, that is a equals 8 and b equals 4 and c equals 9. So you can easily plug these three numbers back into each of these equations and verify that all the equations hold. Okay, so another application, very important, of solving linear equations will be solving differential equations by numerical algorithm. So let's take an example just to give a taste of the problem. So let's say I want to find a function x as a function of t, and then the equation given on this x contains derivatives of x. So let's say x second derivative plus 3 times x first derivative plus 2 times x shall equal to sine of t. And also I want to solve this on the interval from t equals 0 to t equal to capital T. Okay. And then at the two endpoints, the value of the unknown x is given. So these are called boundary conditions. So at t equals 0, x shall be 1, and at t equal to capital T, x shall be 4. So here is a picture. So time and x, and t we're interested from 0 to capital T. And then we know that x at 0 is 1 and x is capital T is 4. But we don't know in between how this x behaves. We only know that this equation holds. So one way of finding solution to such an equation would be using numerical algorithms to find a good approximation to the solution, because sometimes an exact solution might not be possible to find. So what we do would be, we would cut up an interval for t from 0 to capital T into n intervals, subintervals, and then we mark these points, call them t1, t2, and somewhere in the middle let's call this tk, and then the last one let's call it tn, assumingly n is a large number and there are many points here. So instead of trying to solve this x as a function of t exactly, getting the analytic expression, we now find good approximations to the value of x evaluated at this tk. So this we will call xk, which now is a number. It is an approximation to the x at tk. And then we will rewrite the equation here, expressing the derivatives in terms of the values at these points, and this is called finite difference. Okay, and we will end up with many equations for these derivatives, one at each point of tk. Okay, so in the end we have a large system with many unknowns and equations, and we want to solve it, and we will find the values of xk, an approximation to the exact solution. Okay, a little bit detail. Let's denote epsilon to be tk minus 1, which is the step size between two of these t's. If you use a uniform grid, meaning you cut them equally, and then the size is just capital T over how many intervals you cut. And then we'll have x0 is 1, xn is 4. These are the two kind of boundary conditions. And in the end, we will have a system of equations from t1 to the last one, that is tn minus 1, each one will have a equation which this is derived from find a difference to represent the second derivative and the first derivative. Okay, so which is beyond what we cover here, so I'll just write this out. So for each k, you will have an equation like that. K goes from 1 to 2 to n minus 1. So imagine you want a pretty accurate solution. Then you should choose this number n pretty large. Let's say 1,000 or 10,000. And then immediately, easily, you end up with a system of 1,000 or 10,000 equations. Okay, so now let me go through quickly of all the things we will cover in the following lectures. We'll cover matrices. We'll do addition and multiplication of matrices. And we will find inverse and transpose of a matrix. We'll talk about some special matrices, elementary matrices, the inverse of a matrix, how to compute it, and then we will consider the matrix multiplication as a linear map. That is, it takes a vector x and you multiply a over it and transfer it into a different vector. And then we will use matrix algebra to solve systems of linear equations. We'll talk about some theoretical aspects of it. We'll discuss existence of solution, uniqueness of solution, and we'll touch on computational methods. Some linear systems might not have solutions in the normal sense. So in those cases, we are interested in finding an approximation to the solution that is the best one. And there we will use a concept of perpendicular projection. So in a graphic sense, we can look at this picture and see that the solution is, let's say, is this vector b is my solution. But I am looking for the solution in this domain, a subdomain of, for this subdomain of 3D, we can consider it's in a plane. And then this vector b here is not contained in this plane. So what you can do would be you define a concept of orthogonal, perpendicular. So you take this vector b here, you project it down perpendicularly, find its image, we call it p, and then this p here will be the best approximation to this b in this domain w. So this leads to the so-called inner product spaces, because you need that to define the concept of orthogonal vectors and subspaces. And of course, we'll talk about perpendicular projections, orthogonal bases, and then the famous Gram-Schmidt's algorithm you might have heard, and then also matrices that are called orthogonal matrices. So one example in that direction will be the least square approximation. You are probably somewhat familiar with that. So the goal here, let's say you have a bunch of experimental data and you want to fit in a function, and you know that your function is a linear function, that is y equals ax plus b, and the graph of this in the xy plane is a straight line. And you have a bunch of experimental data. These are the red dots. Let's say there are k of them. And then we will want to find this constant a and b. That means the slope and the starting point, such that this straight line best fit the data. So you know that these data, the red dots, should not be all lined up in a straight line. Otherwise, your lab teacher will be very suspicious that you cooked the data. Okay? So some will be above, some will be below, and you will want to find the line going through it, straight line, in a best possible sense. Okay, so that's a typical example where you don't have a solution, and now you're going to find a best approximation. And there's another application we'll be looking at approximating a function. Say you have a function y equal to an f of x. It's not a straight line. It bends a little bit on the interval from x1 to x2. And you are interested in approximating it with a straight line in the best possible way. So this line would kind of go through your function in the graph, but some parts of the function will be above, some will be below, and how to do this in the best possible way. So another topic we will cover is something called the determinants. We'll go through definitions, properties, and some applications of the determinants. So one property of the determinant is the following. If you have a vector of length 2 in a two-dimension space x1 and x2, and you have two vectors v1 and v2, then the determinant of that and the amplitude of that determinant equal to the area formed by these two vectors and the area of the parallelogram. Okay, so here if v1 is like this, v2 is like this, and you can form a parallelogram, and this area, the gray area, will be the absolute value of the determinant. And depending on how you arrange v1 and v2, the determinant can be positive or negative. And then in 3D, these vectors live in a 3D space, and then the determinant of a matrix 3 by 3 like that would exactly equal to the positive or negative of the volume formed by these three vectors. Okay, so you take two, form a parallelogram, and you extend it in the direction of the third one. So we will also study eigenvalues and eigenvectors, and then using that to put a matrix in diagonal form and applications of that. And for example, we'll also learn to do the following. Given a matrix A, we'll find the formula to compute A to the power n for every n. Okay, so some special matrices would deserve some attention from us. These would include symmetric matrices and the diagonalization by an orthogonal matrix. And then another is positive definite matrices and quadratic forms of them. And some applications of these concepts will be finding local maxima and minima of a function of several variables, and then the second derivative test. We will also learn SVD, singular value decomposition, and we'll apply that to compressing data so that the memory space needed to store these data will be much less. Okay, so let me end by giving you some more applications, just like brief overviews of what these applications will end up into linear systems. Okay, so the first one will be applications in biology, growth models for various kinds of interacting populations. For example, the famous predator-prey model. Okay, so we can consider that xk, let's say number of foxes on year k, and yk will be number of rabbits on year k. So foxes are predators and the rabbits are prey, and then the fox will eat the rabbits. But then a fox also needs the rabbit to survive. So you can give a progression of the population. So at year k-1, let's say the population is given, and then after 1 year they will change. How would that be? So they will depend on their previous years, and then on both of so xk will depend on xk-1 and yk-1 also is yk. And assuming them to be a linear relation, we can write this out. Okay, and then you are interested in how the population will evolve as k grows. Another example is in probability and examples of Markov chains. And applications will be like wealth distribution across various generations, and also in the store, the queue size at a counter. So one curiosity could be in differential equations. Tangentially related would be something we probably are familiar with, called Fibonacci numbers. So these are this sequence, famous sequence of numbers. And given the first two, 1 and 1, and then the next one is generated by adding up the previous two. So 1 plus 1 will get 2, and then 1 plus 2 will get 3, and then 2 plus 3 will get 5, and so on and so forth. So this can be compactly written in the following expression. So we have x1 is 1, x2 is 1 as the initial condition, and then for later subsequent numbers, xn for n is 3, 4, 5. Any xn will equal to xn minus 1, the previous one, plus xn minus 2, the second previous one. So we are interested in how fast do these numbers grow. And then, for example, what is x with index 1 million? What can we say about that quantity? So surprisingly, we have an explicit formula for xn for any n, and that can be obtained by actually computing the powers of this particular matrix. A, which is 1 and 1 and 0 and 1. It's 2 by 2. So this is something we will cover later on in the course. So if you are fascinated of Fibonacci numbers, you can look forward to that. Here is another application of using matrix algebra, which applies to the ranking of web pages on the internet. So let's say we have 5 experts. Let's call them Alice, Ben, Chris, David, and Eric. They are all experts on wild mushrooms in Pennsylvania. And then their websites are linked as follows. So A, B, C, D, E. So A links to E and B and C. And then B links to E. And then D links to B and C, where the arrows are indicating the linkage. So how shall we rank these pages? Which page shall be more important? Namely, which of these 5 experts are the best expert? So one can generate this matrix of linking. So A, B, C, D, E here, and A, B, C, D, E here. So the entrance of this matrix will be 0 if there's no linkage. And then if there is any linkage, let's say A is linked to B, then from A to B, this element here then is marked with 1. Okay, and then we also see from A to E, that's marked 1, and from A to C is marked 1, and the rest is 0. And that's how you fill in this matrix. So we have a square matrix 5 by 5, storing the informations of who links to who. So how do we utilize this to find out who is the leading expert? Probably you can already see from this diagram here that Ben is the expert because all the others are linking to Ben. And then how do you rank the second and third or fourth? How do you do? So actually this leads to an eigenvalue eigenvector problem for this 5 times 5 matrix. So if you're interested, and this is a paper on SIAM Review, and it is an algorithm used by Google to rank different websites. Okay, so that's all for today's lecture. I hope I gave you some idea of what to expect in the following lectures. And I hope you enjoyed this one, and I will see you next time.